think. All right. Hello, everyone. Welcome to this debate on sparks versus embers. So the proposition for today's debate is current LLM scaling methodology is sufficient to generate new proof techniques needed to resolve major open mathematical conjectures such as P is not equal to NP. So for the debate, I would like to introduce our participants. In favor of the proposition is Sebastien Bubeck. Sebastien did his PhD in applied mathematics at India in Lille, France. He was assistant professor at Princeton from 2011 to 2014. Also during that time, he was visiting scientist here at the Simons Institute during fall of 2013. He joined Microsoft Research in 2014 and spent 10 years there. Was most recently as VP of AI and distinguished scientist. He first joined the theory group at Microsoft Research, working mainly on convex optimization, online algorithms, and adversarial robustness in machine learning. He's received numerous best paper awards for papers on which he was co-author, most notably at NeurIPS and STOCK. Pertinent to today's debate, in the past few years, Sebastien started working on understanding how intelligence emerges in large language models. He led the effort at Microsoft to develop the phi class of small language models and was a co-author on the Sparks of AGI paper about early experiments with GPT-4 and is hence on the Sparks side of the debate. He now works at OpenAI. I think you just started there?
Yes, 5 weeks ago.
Yeah. So, and speaking against the proposition is Tom McCoy. Tom did his PhD in cognitive science from Johns Hopkins University and a postdoc in computer science at Princeton with Thomas Griffiths. This year, he started at Yale University as assistant professor of linguistics, where he works on computational linguistics, cognitive science, and AI. Tom is interested in how people and machines learn and represent the structure of language. He wants to understand the types of computational machinery that can explain the linguistic abilities of humans and whether we can instantiate these abilities in machines. And what can the success of, say, LLMs tell us about human language, and how can ideas from linguistic and cognitive science help us to understand neural network language models? He also works on combining neural networks with other modeling approaches, such as Bayesian models. And to make a case for why Tom's on the embers side of the debate, in September 2023, he co-authored a paper titled Embers of Autoregression, Understanding Large Language Models Through the Problems They Are Trained to Solve. And it was followed up with a paper this year too, which was an analysis of OpenAI 01. So the debate has a very, very specific format. I'll just briefly tell you about that. More importantly, let me just establish some of the terms that are there in the title. When we talk of current LLM scaling methodologies, we're talking about everything in a modern scaling law, meaning training time compute, test inference time compute, training data, all of which can be feasibly achieved in the next X years, where the proponent or the opponent can take a position on a reasonable value for X, signaling something in the near future. So not 100 years from now. The proof technique should be certifiable by human experts with any means at their disposal, including compute and or grad students. Difficult open mathematical conjectures, those that most human experts think cannot be resolved with current proof techniques, such as P is not equal to NP and the Riemann hypothesis. So the format itself will be both Seb and Tom will have 5 to 7 minutes each to make their case in favor and in Tom's case against the motion. After that, we will have 2 rounds of 3 minutes each, where you will get to respond to each other's opening statements and then to arguments you make in your response. The key thing about this debate is that there will be no interruptions. The person speaking has the mic. The other person on the debate stage will not interrupt, neither will the audience. And this is all to figure out whether they can sway us based on the arguments that they're making. And but before that, before we start, we would like to do a pre-debate poll. And there's a QR code here. If you just scan that, it will take you to a website, a Slido website, and just register your priors. And
I was hoping it would be a show of hands so that we could know.
No. We will. So no one gets a sense for what the priors are.
Okay.
And
we can fix the timer to answer this. If we're taking the poll, you are X is a variable. Oh, X is a free variable.
X is a free variable in the reasonable.
It's okay.
This isn't that scientific.
Yeah. We will resolve it.
All right. Has everyone registered their decision? Cool. Okay. So the other thing about the format, Fanny here will be keeping time, and we'll start a timer for each person at the 5-minute mark. She will ring the bell once to give you a 2-minute warning. And then at 7 minutes, she'll just start making a lot of noise with the bell. So you have to stop. And then we switch to the other person, right? Yeah. So for the other discussions where you have 3 minutes each, you'll get a signal at when there's 1 minute left, and then at the 3-minute mark, loud noises. So so with that, oh, by the way, my name is Anil Ananthaswamy. I'm the journalist in residence here at Simons for fall and spring. And even though my bio on the website seems to say Heidelberg Institute, that's not true. I used to be there, not anymore. So, so with that, let's have Sebastien present his case in favor of the motion. Fanny, you're going to start the timer? Oh, you're. Okay.
Okay.
Oh, there. Okay.
Great. Okay, awesome. So I'm really happy, to be here. It's always a pleasure to be in this place and with so many familiar faces. I'm really looking forward to see what you respond to what I have to say. So maybe I want to start by going back to some of the definition. When we talk about scaling, what do we mean? Anil said, anything that could come up in the next 5 years. So of course, the main tool, as you all know, is a next word prediction on a very, very big model. That's one aspect of scaling. That's, of course, not what I'm saying. I'm not saying that just scaling up, making a bigger model on a bigger data set with just next word prediction, that will at some point create a machine where you can just ask, prove me the Riemann hypothesis, and then it goes and write a proof. That's not what we're talking about, okay? Just to make sure. And to emphasize this point further, you can look at the gap between GPT-3 and GPT-3.5. GPT-3, that was a big model trained on the web, next word prediction, very, very classical. What could that model do? Well, it could write kind of shitty poems, maybe, not that great movie scripts. Of course, for us in this room, it was still completely shocking that it could do that. I mean, really, we have no tools to understand what's going on there. But GPT 3.5, that's the one that really shocked the world, that really made a big impact that can start to do stuff. And what is the difference between GPT-3 and GPT 3.5? It's the post-training. And the post-training, this is a crucial aspect where you're trying to control the model, really try to extract all of the intelligence that has been imbued with next word prediction. So next word prediction imbues the model with a lot of intelligence, and post-training extracts it and put it to something that we care about, some tasks that we care about. For GPT 3.5, it was chat. Okay, it was just having a chatbot. But now we have post-training techniques that can do a lot more than just extracting a chat model out of the big next word prediction machine. For example, we have reasoning post-training with the O series of model, and that's a completely new style of post-training. Okay, so this is what I'm talking about with scaling. Now, before trying to make the case for why I think that big major open problems could be resolved in the next few years, I also want us to just take a few minutes to take stock of the progress that has been made in the last few years. Because this progress, I think, is nothing short of miraculous. And I'm just going to talk about benchmark. I'm not a big fan of benchmarks. This was the whole point of the Sparks paper, to go beyond benchmark. But for the sake of time, let's focus on benchmarks. So in the last few years, there is one benchmark that really rose to the top, which is MMLU. Somehow, all the big CEOs, they started to, Mark Zuckerberg started to talk about MMLU as kind of this really way to demonstrate the intelligence of a model, whether you're at 80%, 85%, etc. GPT-3 was at 50% on this benchmark. And MMLU is like kind of high school level science question style. Humans are at 90%. Okay, GPT-4 was already at 86%. O1, we're talking about 92, 95. I don't exactly know, but it's now it's basically in the noise level of the benchmark. So this benchmark, even though it rose to the point where it's moving stock market, it's moving the world economy. That's it. This benchmark is gone. It doesn't matter at all anymore. It's completely saturated. Okay, so we have to look beyond. Now, just recently, there was a study that came out on medical diagnosis, comparing human doctors to GPT-4. Human doctors on that benchmark were getting 75%. Okay, so 3 out of 4 were correct. GPT-4 gets 9 out of 10. Okay, on medical diagnosis, like this is something that we care about, I care about in the real world, And GPT-4 is already beyond humans. Now, in that same study, they are already foreshadowing what happens with O1 and saying that there are now cases where human doctors are at 50% and O1 is at 90%. I mean, this is just, completely incredible. Now, closer to what we're talking about today, there was a math benchmark, which is high school competitive mathematics. And that quickly got saturated. Now we're talking about AMI. So AMI is a new benchmark that, OpenAI, for example, is using to benchmark the new O models. So AMI is this test to get into the US team for the IMO. O1, so GPT-4 is at essentially 0%, maybe 5%, maybe 10%. It's essentially 0%. O1 preview, I think, is already at 50%. You can see it. It's going to be at 90% next month, in 2 months, And the IMO gold medal is going to be, okay, I still have some time. And the IMO gold medal is going to be, I don't know when, but, very soon. For sure next year. There is just no question given the current trend. Okay, so this is the definition, taking stock of where we are. Now, what is the real argument? The real argument is not very deep and pretty simple. So the way I like to frame the discussion, and this is not by me, I don't know actually who came up with it, is in terms of AGI time. So how much, do you have an AGI second? Do you have an AGI minute? Do you have an AGI hour? Meaning, can you mimic what a human would do if they have just a few seconds to think, if they have an hour to think, if they have, a day to think? I think GPT-4, to me, I mean, that's what I wrote in Sparks, it's very clearly an AGI seconds. So it's clearly as good as basically any human who has just a few seconds to think. If you are, maybe it's already getting into AGI minutes in some cases, for example, in coding, certainly not AGI minutes in mathematics. Okay, that was not the case. It was AGI seconds in mathematics. Now, when we go to O1, we're already talking, I think it's AGI minutes, like uniformly, and maybe it's already AGI hours in coding, for some math problem, not for you guys, but for the vast majority of the population is already AGI hours for mathematics. Like what will it take, to resolve big major open problems is to have AGI weeks. I mean, that's it. That's all you need. You don't need anything else. If you have AGI weeks, then you have it. And you see the trend. We went AGI second, AGI minute, AGI hours. Next year, will we have AGI day with, singular? Yeah, maybe. That's what an agent would be like. Will 2 years from now, will we have AGI days? Yeah, probably. 3 years from now, AGI weeks. So that's my argument.
Great. Well, Tom, your response or your opening statement against the proposition.
Yeah, well, thanks so much to the organizers and the Simons Institute for making this possible. I'm really excited to have the chance to talk with Seb. His Sparks paper really had a big impact on me. It was really the first thing that got me, or convinced me that we need to start taking LLMs seriously for tasks beyond language. So it's clear that LLMs are extremely impressive. For this debate, the crucial question is just how impressive are they? Are current approaches successful enough that when we scale them up, they will be able to resolve these unresolved problems in math? And so I'll be arguing that the answer is no, scaling current approaches will not be enough. And so to start, I think it's helpful to think about what will be required in order to discover these new proof techniques. So first, it will presumably be necessary to have some sort of creative leap something that can provide the new idea that will make these new proof techniques work where all previous proof attempts have not worked. And then once you have that new idea, it will also then be necessary to have some long sustained reasoning and planning in order to develop that technique into the full-scale proof that has the level of rigor that a proof requires. And both of these components pose serious challenges for current approaches, challenges that scaling alone will not be sufficient to overcome. So to start out on the topic of making creative leaps, this is a major challenge for current LLMs because their abilities to handle a task are okay.
Oh. Yeah. Shall we add 15 seconds to the speaker's time?
Are we okay? So it's a tsunami, right? It'll take some time. Okay, all right. So the clock is stopped. You can start now.
Okay. Yeah, so as you can see, intelligent agents sometimes have to deal with novel scenarios that require creative leaps or adapting to new scenarios. And the reason that this poses such a challenge for current approaches is that their abilities are heavily influenced by how well represented the task in question is in their training data. So this is the main point of our Embers of Autoregression paper. So to give one example, if you ask GPT-4 to count how many words are in a list of words, if the length of the list is 30, it gets an accuracy of 97% on lists of that length. But if the length of the list is 29, it gets an accuracy of 17%. Presumably because in pre-training data, the number 30 is used much more frequently than the number 29, just because humans like round numbers. Or to give another example, LLMs are much better at sorting a list of words into alphabetical order than reverse alphabetical order. Again, presumably because alphabetical order is much more commonly used than reverse alphabetical order. So GPT 3.5 gets an accuracy of 76% on alphabetical order, but 15% on reverse alphabetical order. And crucially, scaling, at least the scaling that's been done so far, has not resolved this issue. So when you go from GPT 3.5 to GPT-4, GPT-4 does quantitatively better on both types of sorting, but qualitatively, it still does much better on the common type alphabetical, where it gets an accuracy of 82%, than reverse alphabetical, where the accuracy is 32%. So the issue here is that we have clear evidence that scaling brings quantitative improvements to LLM abilities, but in order to have the sorts of creative leaps that are needed for new proof techniques, we need qualitative changes. And the importance of frequency is particularly important here because by definition, a new proof technique will have a frequency of 0 in the training data. So no amount of scaling will give the LLM experience with these new proof techniques. Now, to be clear, I want to clarify that I'm not claiming LLMs are simply memorizing. This is demonstrably false. There are many examples of them doing things that, handling examples that were not in their training data. And many of my favorite examples of this come from the Sparks paper, like being able to write a proof that there are infinitely many prime numbers where that proof takes the form of a Shakespearean scene, for example. But it's important to keep in mind that not all generalization is created equal. So the really impressive examples of generalization that I'm aware of in LLMs take the form of taking two familiar ideas and combining them in a new way. For example, the idea of a Shakespearean style being combined with the topic of a proof about prime numbers. But that type of generalization is not what is needed to solve these unresolved conjectures in mathematics. Instead, what's needed is an entirely new idea, not just combinations of familiar ideas. So that's the concern about making creative leaps. The other concern I raised was once you have this creative leap and have your new idea, you then need to build out that idea into a proof. And for complex mathematical conjectures, writing such a proof can be quite a major endeavor. Proofs can run to be dozens or hundreds of pages. And now there has been a lot of progress recently in enabling LLMs to reason for longer periods of time. So this has come with the advent of approaches like chain of thought reasoning, where LLMs generate multi-step reasoning pathways. But the important issue that arises here is that the current LLMs are susceptible to producing factually incorrect content, often referred to as hallucinations. And the issue is that when the length of the proof that needs to be written is very long, even if we can really reduce the rate of hallucination substantially, as long as that rate remains non-zero, when the proof becomes long enough, the odds of having an error somewhere in that proof will become essentially certain. And as long as there is a flaw somewhere in that proof, that invalidates the proof, because as the saying goes, a chain of thought is only as strong as its weakest link. Yeah, so this is another area where, in order to overcome this issue of reliability, this will take a qualitative change, not merely the types of quantitative benefits that scaling seems to provide. So overall, just to summarize, there are two critical factors that impede current approaches from being able to solve unresolved conjectures in mathematics. The first is the need to provide creative leaps that create qualitatively new ideas. And the second is the ability to have sustained long-term reasoning and planning over the course of dozens or hundreds of pages. I am very optimistic that AI writ large as a field will be able to resolve these problems, but scaling will not be the technique that achieves that.
Under time too, fantastic. Well, thank you both for your opening statements. And when I looked at the Sparks versus Embers title, it lends itself to so many puns. And a lot of people were hoping for Sparks to fly out here. So far, it's been very cordial. So maybe now these two rounds of back and forth will set us up for some Sparks. So Sebastien, you have 3 minutes to respond to Tom's opening statement.
Yeah, I plan to keep it cordial though. So no, but I would like to push back on basically almost everything, except the Embers paper itself. I mean, I agree with everything that's written in there, and I will explain why I still push back on the conclusion you draw from this. So maybe the first thing where I want to push back on very strongly is you said that one generalization capability that those models have is to combine two different ideas, and that this will not be enough to do something novel. I mean, I'm asking all of you, do you think you're doing a lot more than combining existing ideas? And maybe, there is a little bit of jittering around, some random walk in the space of ideas, and sometimes you step a little bit outside. At least for me, when I look back at what I'm doing, I think it's mostly combining. And then, yes, there is a little bit of randomness added to it. In fact, I have written many papers where I have taken somebody else's result and then realized that actually what they were doing was only combining existing things. So maybe, in their mind, they were discovering it through other means, but actually you can rewrite it in a way which is just combination. So I believe that combining things is extremely, extremely powerful. So that's the first pushback that I want to give. Now you say, also that as the reasoning gets longer and longer, it's bound to have some mistake in it. Again, I mean, how many papers, with more than 50 pages are entirely correct? Very, very small number. Now, it doesn't mean that the result is not correct. Of course, the result will be correct. Once the mistake is pointed out, you're like, oh yeah, of course, no, but you can do X, Y, Z, and you can expand on this. So there is this interactive process that happens with human beings too, and it will happen with AI. We're not saying it's like, I could envision a future where there is a community of AIs working together, and maybe some, it's kind of a multi-agent setting, where some are reading the papers that somebody else, some other AI has written, pointing out the mistakes, and the guy responds, etc. So this is absolutely a plausible future. Now, just more down to earth, on the Embers paper and the fact that there are more mistakes when things are not well represented in the training data. Of course, this is absolutely a true statement, but it's a true statement for the base model. And it doesn't mean, and it's a base model at test time. It doesn't mean that it's not in there. The capability can be in there, but the network just has no, there is no pressure on the network to express that capability, because it's just not useful for next word prediction, because it's so lowly represented in the training data. But then again, you can use post-training to extract those capabilities out. And I think you say it in the embers paper that it is only about the base model. If you do post-training on it, some of the conclusion would change. Okay, I will stop here.
Great. Tom, your response to Seb's opening statement or anything you want to respond to?
Thank you. Yeah, so I guess first regarding this comment about the base model versus post-trained models. So our argument is definitely based on the base model. So the argument is about how being trained on next word prediction or autoregression makes models predisposed toward high probability sequences of words. So that part is, yeah, I agree with. But empirically, we have found that these effects that arise from pre-training continue to persist through post-training. So most, in fact, I think all of the models that we analyzed were post-trained models that nonetheless continued to display these embers of autoregression. And even we had this follow-up about O1, which has been very explicitly optimized for performing robust reasoning. And it did perform quantitatively far better than the previous models we looked at, but it still had these qualitative effects of performing better on, alphabetical order than reverse alphabetical order and similar things. So it does seem to me that even these post-training methods are not sufficient to override the model's fundamental nature, its fundamental roots in autoregression. So my prediction would be that to fully eliminate those concerns, it will be necessary to have systems that are, even starting the pre-training phase, explicitly and directly trained on reasoning, because as it stands right now, the reasoning that models do is effectively tacked on at the end. It's a very important step, but in terms of number of training flops and things like that, it is far less. And so to get the type of robustness we need, I think that will require some qualitative change. Yeah, another factor I'd like to raise is that in addition to being able to combine existing ideas, another important step of the process is figuring out which ideas need to be combined. So most of the cases I'm aware of these really impressive cases of combining two ideas are situations where we tell the model, here are two things, we want you to combine them. But I do expect that this first part of knowing which things would be productive to combine in a way that will yield new proof technique is a much harder problem. And in addition, I completely take the point that many brilliant insights that people have, including ones that have led to previous famous proofs, did involve combining existing ideas in impressive ways. But there is also a spectrum of how novel or how creative an idea is. And the ones that have been successful at resolving unresolved problems, like Fermat's last theorem, are really celebrated for being extremely, extremely creative and using previous techniques in very novel ways. And so one other observation that is relevant for this, is that the 1 minute? Okay, sorry. Okay. So I'll stop there then.
So yeah, Seb, your 3 minutes begins now. You can respond.
Yeah, so maybe I want to take the discussion in a slightly different direction, and I will reply to this extreme creativity in my closing statement. It will take me just more than 3 minutes. So in a slightly different direction, and it's not directly answering, the debate. There is going to be a phase, and this is for sure. I don't think it's up for debate, where before the AI does solve a problem on its own, it's going to collaborate with all of you guys. And I just want to share a personal experience that I had myself just in the last few weeks with O1 or O1 plus epsilon on a research problem, which I know is not out there because it's a paper I have written and it's a draft in my Dropbox, and I just didn't publish it yet. So I know that it's not in the training data. And this is, you will see, it's a very fun question. It's just about how long can be the gradient flow of a convex function. Okay, so it's you can think about it. It's a very nice question, and I asked this question to this O1 model, and what it came up with, it thought for a long time, and then it made a connection with what's called self-contracted curves, which are a type of curves that exist, and is not necessarily directly linked to this. And it explained to me why, it thinks that this would be a good idea to connect those two things. It gave me the bound that exists in the literature, etc. When I was working on that problem, it took me, 3 days to make that connection. So at the very least, it would have accelerated me by 3 days. And now you take this is just a very basic current model. Take this, next year, I have other anecdotal evidence of people, top people who are, maybe some of them are sitting in this room, who were stuck on some lemma, asked O1, and O1 made a connection and, helped them solve this problem. So this is not in the future. This is not hypothetical. It is happening right now. It's the same story as with the medical diagnosis. It's the same story in every field right now, that AI is, at the very least, going to be almost an equal with us. Okay, I'm going to stop here. I don't need
You have 1 more minute.
3 minutes on this point. Yeah, I think I'm good with
You're good? Okay. Tom, you don't get the extra minute from him. You just still have your, your time starts now.
So I completely agree that AI is already at the point where it can very helpfully collaborate with humans. But I do think that does not necessarily entail that it will be able to get to the point of, on its own, without that human in the loop, being able to make these novel contributions to mathematics. And I do think it's also important to recognize that in order to resolve some unresolved problem in mathematics, it's not sufficient to merely be as good as humans, but it actually has to be better than humans in some sense, or at least better than the humans we've come up with so far. Hopefully, a human would be eventually able to solve these problems. I guess one other type of factor I would like to raise is just the practical demands of scaling to the level that would be necessary. So there is the in principle question of, given unlimited time and unlimited data, would scaling eventually be able to get there? But if we bring it down to the practical question of, is there some number X such that after X years, scaling will have gotten us there, then I think there are some important practical considerations that come to mind. So first, people are already becoming concerned about whether there will be enough data to continue data on the internet, for example, to continue the level of data scaling that exists. So this is one of the reasons why test time scaling has become so exciting, because it gives us a different type of scaling that might not depend as much on pre-training data. But even for the test time scaling or number training epoch scaling, there is the concern there that many of the scaling laws that have been observed, that is the systematic ways in which performance improves as you scale, are logarithmic, meaning that we'll need exponentially more data or exponentially more inference time in order to continue with seeing the performance gains. And at some point, that exponential growth might become intractable.
Yeah, 1 more minute.
Okay, and I guess I'll just raise one other point, which is in addition to being able to recognize how to use some familiar idea in a novel way, it may also be important for AI systems to be able to robustly use that familiar idea in a novel way. And we also do have evidence that AI systems perform much better at using some idea in a familiar way than in a novel way. So one example of this, you give GPT-4 a number and tell it to multiply that number by 9/5 and add 32, it gets around 11% accuracy. But if you say, I want you to multiply this by 9/5 and add 32, and by the way, that's the conversion from Fahrenheit to Celsius, now that accuracy jumps up to 62%. So it's the same computation, but just recognizing that it's a familiar setting is enough to really improve performance.
It's kind of the same for humans, but
Well, so we're now at the stage of closing statements, and Tom, you'll have first go at the closing statement. But one request from both of you: you talked about post-training, and also referred to that scaling might not involve the current methodology, but there might be other things. So if you could touch upon what kinds of things we might be scaling, and also what kinds of post-training might be involved to get us to this point, either of you. And Tom, you have first go at the closing statement.
So when I'm speaking skeptically about large language models, I'm often reminded of this joke. So the joke goes, a group of friends is walking through the park when they come across a man playing chess with his pet dog. So they go up and say, wow, it's amazing that your dog knows how to play chess. And the man replies, not really, he usually loses. So the point of the story is it's kind of silly for the man not to be impressed by his dog, because it's amazing if a dog can play chess at all, even if it's not that good at it. So I feel the same way criticizing large language models. It is truly amazing that they can do all of the things that they can do, even if they do many of these things imperfectly. So LLMs are amazing, but it is very important not to get carried away. They are amazing, but all of their abilities have to come from somewhere. And as far as the strongest evidence I'm aware of is concerned, the somewhere where these abilities come from is the training data. Just over and over again, we see very clear cases of LLM abilities being tightly tied to frequency in the training data. Under this viewpoint, the fact that LLMs have such broad and impressive abilities might be more a reflection of the diversity of their training data rather than the ability to have deep generalization abilities. And this is relevant for this debate because this means that if we want LLMs to be able to do something that is deeply and truly novel, this will require something different than the current paradigm. Merely scaling the current paradigm will not get us there, because what is needed here is simply not present in the training distribution. Now, it is certainly possible to have a learner that can do things that go beyond its data. So humans provide an existence proof of this. Humans have previously resolved unresolved problems in math. But so far, we don't have evidence of LLMs being able to do that at that level of creativity and depth. Yeah, so I am optimistic that AI more generally will be able to get to the point where it can help us with these unresolved problems, but I'm skeptical that scaling alone will get us there. So I guess to get at Anil's question, some of the critical things that I think will need to be improved, number one is enhanced abilities for long-range reasoning and planning and better long-term memory. And one important point here is that just giving LLMs, for example, a larger memory might not be enough. We also need to figure out how to get them to use that enhanced memory effectively to make sure that it can recognize which information is important in that very long memory context. Second, we will need to find ways around this issue of hallucinations and reliability. One potentially promising technique here would be more streamlined integration with symbolic components like proof verifiers. This other one, I guess I alluded to earlier, but it may also be important to have systems that are optimized from the start for manipulating ideas rather than language. So large language models are first and foremost models of language. Their major initial pre-training stage is based on language prediction. And more recent approaches absolutely do have additional stages of fine-tuning and post-training, but it remains the case that the base model is fundamentally based on language. And so this leads to this effect where the ability that LLMs have to deal with ideas is something that has to emerge indirectly. And I think this is a likely explanation for why so much of LLM reasoning continues to be relatively brittle or influenced by probability. And to get around that issue, it may be important to have the model be directly optimized for reasoning rather than starting out with language. The last thing that I think may be very important is whatever it takes to handle this hurdle of creativity, which is definitely very puzzling. I think no one has the answer to what exactly it takes to be creative, but a couple factors that might be important here are abilities for abstraction and for analogy making, because abstraction and analogy making both enable you to see familiar ideas in new ways that can enable you to draw connections that have not been drawn before. So all of this is much easier said than done, but I do believe that these new types of innovations, which will require continued human ingenuity, will be what we need in order to have the sparks of artificial general intelligence finally take hold and ignite.
Okay, well, Sebastien, your closing statement.
Yeah, so it's funny because, I mostly agree with what you said. It's just, again, I draw different conclusions from it. So again, you said two things which are kind of obviously true. So one is it's all about the training data. Yes, absolutely. It's all about the training data. And the second, which was a key point of the Embers paper, is that it's all about the objective. What is the pressure that you put on the model? What is it that you're trying to extract from this training data? So in the training data, of course, right now there is archive. But if you're just trying to predict the next word on archive, yeah, you're not going to make much sense of it. I mean, you're never going to be able to really understand what's going on there. But what you can do is that you can train the model to try to really think deeply about those archive papers. And this is what this new, O1 paradigm is doing. So of course, it's very frustrating that I can't tell you exactly what it is, but it's, it's at a high level, it's just reinforcement learning. Like you just have the model think about those things for a much longer time than usual. And again, it's just like us humans. I mean, the way I think about it is the pre-training on the web. It's a little bit like when we go through high school, up to until high school or maybe early undergrad. You're just exposed to a lot of things, you expand your knowledge a little bit. And then you go to grad school and now you drill, very deep, you think for a very long time. You first year of grad school, you pick a paper, you read it, you spend a month on it. That's what those models are currently doing. They are literally being trained to think very, very hard about one piece of content. And I just don't see any obstruction once you start doing that. So that's my first point. The second point is, and this is a really important one, a crucial one. Everything that we're doing right now, including this O1 paradigm, is extremely scalable. And this word scalable, I don't like it too much because it can mean so many things. So I'm going to use a different word. It's really, everything is kind of emergent. Nothing is hard-coded. It's anything that you see, out there with the reasoning, nothing has been done to say to the model, hey, you should maybe, verify your solution, you should backtrack, you should do X, Y, Z. No tactic was given to the model. Everything is emergent, everything is learned through reinforcement learning. This is insanity. Once things start, and this is why I was so shocked with GPT-4 and why I wrote the Sparks of AGI paper, is because once things start to be emergent like this kind of capability, how can you tell what is the limit to it exactly? It's very, very hard to say. So this is really, really important. It's scalable. Everything is emergent. And there are like 10 more approaches that you can try. So this is the crazy thing, is that we're still, even the O1 paradigm, it's very simple, it's not that crazy. So the fact that there are 10 more directions that you can keep pushing, even if one of them gets stuck, there are other avenues that we can use. One of them, of course, is synthetic data. This is what I have been doing with the Phi series of model with the folks at Microsoft. Synthetic data, now you suddenly control what is it that you're feeding those models. You can literally write a curriculum for the AI. I mean, that's what we did with Phi. We wrote curriculums for the AI to learn. And we can get it, let's say, on GSM 8K to get to 95% without contamination, with like a few billion tokens, as long as you craft a good curriculum. And this is still in the very, very early days of this. So there are just so many avenues that we can keep pushing on. And then the last point is, again, similar to your last point about what is really creativity. So to me, when I look at, my own work and other people's work, like the really beautiful moments, the real creativity moments are when you recognize patterns. Again, recognizing patterns, it's kind of like combining things, but it can be combining things at a different scale. It's not just you're combining two ideas. It's like you suddenly see that many, many things relate to each other in a very, very novel way. So this to me, this is what coming up with a good definition is all about. A good definition captured, possibly infinitely many things into one, single sentence. When in the title it says P versus NP, it starts with a good definition. It starts with Turing machines, it starts with all of those things. So coming up with those good definitions, it's all about recognizing pattern. It's all about abstraction. Now, the key point is that this seems to be a teachable skill. You could give a bunch of examples. You can craft a bunch of examples of what it is to come up with a good definition. And once you will have imbued the model with this capability of abstraction, of coming up with good definition, and you combine it with everything else that we said, I just see no limit to what those models could do.
Perfect timing. Well, thank you very much. So that's the end of the formal part of the debate. We have a post-debate poll now, and you can scan the code again and register your vote again to see whether your minds have been swayed. Did sparks fly, or did the embers get quenched, or whatever you want to think about. And once we have the poll done, we'll have our discussants on the stage to further enlarge the conversation. The poll results will come out after the next round with the discussants. Done? All right. Is that more tsunamis coming our way?
Yeah, so I totally looked this up, and there are two alarms. One is the government alarm, and then there's a UC Berkeley alarm. And the UC Berkeley alarm has not yet been signaled, right? So UC Berkeley is not.
So UC Berkeley thinks we are not in danger?
I know.
Oh, okay.
But as you know, UC Berkeley is often slow in certain systems.
All right. Intros? Yeah. So the polling is done, right? All right. So I would like to welcome two other participants to the stage. When I was looking at this poster and seeing these terms, proponent, opponent, discussant, I was trying to remember what it was reminding me of. And I think the word finally occurred to me. These are all replicants. This is a very sci-fi looking poster. And so anyway, we're all, yeah, let me not go there. So I welcome to the stage Pavel Izmailov. Pavel is currently a researcher at Anthropic. His research interests include reinforcement learning, reasoning, and AI alignment. He was previously at OpenAI, where among other things, he contributed to the O1 models. Starting fall 2025, he'll be joining NYU as an assistant professor. And later today, Pavel is going to be talking about weak to strong generalization. And I would also like to welcome Ankur Moitra. Ankur needs no introduction to this crowd because he's been speaking at this semester about 4 or 5 times now. Ankur is the Norbert Wiener Professor of Mathematics at MIT and the director of the Statistics and Data Science Center. His research aims to bridge the gap between theoretical computer science and machine learning by developing algorithms with provable guarantees and foundations for reasoning about their behavior. So the format now is basically Pavel and Ankur will have 5 minutes each. You can say your piece or you can ask questions of the debaters to clarify anything that you might have questions about. So Pavel, can you have the first 5 minutes?
Yeah, thank you so much. I guess I'll start by saying my opinion. I think I have a pretty mixed opinion in general on this topic. So first of all, I think like there is this point that models are trained on human generated data, and it's kind of hard to expect them to go beyond human level. But at the same time, I think if you think about the data on the internet, it's not just like something that a single human wrote from their mind. It includes a lot of superhuman data in a way, like results of the experiments, for example, in papers. Or yeah, I think one of the cool examples in Seb's Sparks of AGI paper was that GPT-4 trained with text only actually has some kind of vision capabilities on SVGs, which is not something that a human normally can do, just like from reading, the SVG file, making manipulations to it. And so I think the models are just like, in general, to me, the most exciting part about models like language models is that they are extremely good at recognizing structures in the data. And if we have data that is relevant to like extremely hard reasoning, I think eventually the models will be good at recognizing that structure and will be able to do very superhuman things. So, but at the same time, yeah, I feel like, again, with the standard paradigm of just pre-training, by default, I would not expect that the models would spit out like proofs of very superhuman, like theorems that humans cannot prove. But they might have representations that are sufficient to easily go there, I think. And another point I would like to make is that it is possible that humans are actually not that good at mathematics, like objectively, just because we are. It seems like a side effect of evolution in general to do mathematics. Like we don't really need to be good at mathematics. And if we are optimizing heavily for mathematics, it might be that it's like much easier to be very superhuman at math compared to being like superhuman at locomotion, like walking around. Yeah, so I think that's my argument for why I think it's possible that we can go beyond human level. Also, I guess another point is that I think for math specifically, we actually can provide good reward signal for reinforcement learning. Because, yeah, I think you mentioned, Tom, the kind of proof verifiers like Lean, for example, exist. So we can actually ground to something objective. And it's possible to, check pretty complex proofs automatically, and we can like actually train against that reward signal. And we can also probably generate synthetic data with like proofs that are not written down by humans. So we can probably generate superhuman data and do reinforcement learning. And also probably for math, there exists a discriminator generator gap. It might be that it's much easier to check correctness of proofs than to generate proofs. I think it's still somewhat of an open question of like how well we can check proofs with models. But if that's true, then we can do RL with models, like self-improvement type loops, basically, where models check proofs of other models. But I guess like at the same time, I think that like if we think about isolated domains like chess, for example, we have had very superhuman models for a while, like models that are way, way beyond human capabilities. And those are not LLMs. And at the same time, we have LLMs now, which are, it's public that GPT-4 has been trained on like a bunch of chess data in a specific format. And it's kind of okay at chess, pretty good, but like way, way worse than superhuman like AlphaGo or like Stockfish, for example. And I think even with O1, like, again, I guess O1 could have been trained on chess much more heavily, and maybe then it would be approaching like that level, but I think it's hard to tell. I think right now, it seems like these kind of very generalist models like GPT-4 are very far behind specialized models on these like heavy reasoning domains like chess. And to me, it seems very possible that for math, we shouldn't be doing LLMs, actually. We should be doing some kind of smart search in like symbolic space, maybe with LLM assistance, kind of like AlphaProof, AlphaGo, AlphaProof, AlphaGeometry type papers, rather than like, scaling up LLMs. Because a lot of the pre-training data for LLMs, I think, like the vast majority is completely irrelevant to mathematics. It's just, astrology or like news articles, and like that has zero transfer to math. So it seems like maybe not the best possible approach in terms of like financially, scaling to trillion-dollar clusters and then doing RL on top of that. Yeah, I think that's it.
Thank you. Ankur?
Great. So I guess I'll put on my mathematician hat for this. So I have a lot of thoughts in my head. Let me try and put them together in some order. So first, it's incredible what these language models are doing. They're going to change society forever. But I'm not convinced, especially when I look at, a title like the one for this debate. Just to try and add some perspective to this. When we're talking about major problems like P versus NP or the Riemann hypothesis, one of the things that David Hilbert, one of the greatest mathematicians of all time, said about the Riemann hypothesis was that if I fall asleep for 1,000 years, when I wake up, the first question I'll ask is, has it been solved? So we're not talking about, language models that can, help us by proving lemmas, right? These are all things which, they can refine the way that we do mathematics in incredible ways. And I'm really excited about that, right? But the mode of interaction that we're, projecting forward is that they can, know more than us. They can find connections that we don't see. It's not that there is, a 1,000-year barrier, that's just creating this fortress around a problem. And no one has any idea how to get in, even though we have a very good understanding of the obstacles. These are what these problems are about. If someone solves Riemann, it's not a bunch of tricks. It means that some new idea or ideas are in there that are fundamentally going to change mathematics forever. And I'm just not sure why we have so much excitement or belief that, we're on that path right now. Because, a lot of the arguments that people levy about why we're on that path really come down to questions about benchmarks. We heard a lot about benchmarks, and I'm not really here to haggle about benchmarks. But the truth is, like, benchmarks give us the sense of comfort that we're doing better year after year in numbers. But what do the benchmarks mean? Imagine a world where the human species took on some grand challenge like, I don't know, going to the moon or something, right? Wouldn't that be amazing, right? And how would we measure progress towards getting to that goal? Year after year, I fly a ship up in the air and I measure how high it got. That's not how we measure progress for these kinds of things. So for me, the question is, what is it that I'm learning from these models, right? That I could learn at something at the scale that it would take to solve a major mathematical problem. Whether it solves these problems or not, that would be an epic achievement. And I would be so happy if that happens. But when we take literally what they've learned, right? It's, in some settings, it's very powerful. Like if you think about playing strategic games, things like Go, the fact that it can beat human players, there's actually an outcome beyond just, hey, it wins. We actually learn new moves that humans would never have tried. That's one of the really exciting things, is that when we think about, superhuman mathematics, maybe in principle, it could know more than me, know more than anyone else, right? Because it knows all of what we know. And then it can explore much more than we explore just in one particular direction. That would be super exciting. But, for all these things, making prognostications about the future, it's important to remember that we have other modes of evidence beyond just benchmarks and, math competitions, things like this. One of the other benchmarks that I think is really important to keep in mind is that if we're talking about superhuman mathematics, we've already had playgrounds for this for a long time. We've already had notions of what collaborative mathematics looks like, where it's something that's beyond the ability of one single mathematician. They go back a long ways. There are notions like the classification of finite simple groups. This is one of the early examples of collaborative mathematics. No single person, even though it's a deeply important theorem, understands the full proof. But from the very outset, we had an idea that we could take that proof down, break it down into pieces in a modular way, and we would know that all I need to know is this piece, and I can put them together in these ways. But you talk about modern experiments, things like Tim Gowers' polymath project, which solved the density Hales-Jewett theorem. A lot of those ideas about superhuman mathematics are right there in why he proposed the project. Maybe together we would know all of these tools and we could use them. But what's the interface between mathematicians who are working there? It's not about, this lemma that I've never seen. It's about, these tools, how to use them, how flexible they are, what the full extent of how to use them is. And when I think about, are we there yet? Can we just scale up? And if we just achieve these benchmarks and solve all of them, we'll be at Riemann. The point is that there are missing ingredients, like what is the way that you represent knowledge? When you work with grad students and you have them read papers, it's not so that they know lemma 52. It's so that they know the tool. They know how to wield that tool in a new setting. When they're encountering a new problem, they have an idea about whether this tool is useful. No one literally uses that lemma. That's just not how it works.
Yes. Thank you, Ankur. So I think it's probably time to reveal the poll results. We'll see how the initial. Oh, okay, all right. So yeah, please, it's open discussion now, and also you can submit your questions. Is that QR code the same? Yeah. So, which means I should be able to look at that. Can you put the QR code on the? Yeah. So, folks, questions among yourselves. If you have any questions for each other to start with, while we have the audience respond.
Yeah, I just want to say, again, I agree with everything you just said, both of you. I think we're all on the same page on the facts. And Ankur, what you were saying is, it's hard. Okay, sure. Yeah, it's hard. That we all agree with. But I don't know why the fact that it's hard is any kind of limitation. I mean, again, I want to go back to the framing in terms of AGI times that I was talking about, GPT-4 being AGI seconds or minutes, O1 being AGI minutes or hours. Yeah, we don't know, we haven't seen yet an AGI day singular. And suddenly if you go to AGI days, then you need exactly what you were saying, like memory, how do you represent the knowledge to be able to exchange between different AIs. We haven't seen that. And whether you put that in the existing scaling, that's maybe debatable. So I guess my question to you is, are we debating the definition of what it means to scale up the current approach, or are we debating something more fundamental? To me, it's just a matter of definition. Sure, I don't exactly know how to go from hours to a day to days, but it doesn't seem fundamentally different from what we've been doing.
Sebastien, I had a question. In the beginning, you said that scaling just next token prediction by itself might not be the answer. So do you have suggestions as to like, are we talking of, multi-token predictions or using some sort of diffusion models to do?
Yeah, again, it's about thinking harder about a given piece of content. If I think about an archive paper, I don't want to just go through it a couple of times and keep trying to, think about, do the exercise in your head. You read the paper and you hide, the continuation, and you try to predict the next word. And do that a few times over the paper. You're not going to learn very much. What you have to do is you have to take the paper, do experiments, try for yourself to prove a lemma, etc. Like really, basically what Ankur was saying, like try to manipulate the knowledge, try to really interact with the content in a different way. So that's what it will take. And the O1 paradigm is kind of doing that.
Yeah, Ankur.
So I'm not sure what we're debating either. That's okay. We'll have an interesting conversation. So part of it is about, when you set up benchmarks, like there are sometimes a lot of shortcuts to solving those things. So we talked about, benchmarks in medicine. Look, these things will be amazing, right? But we've already learned a lot of lessons about how setting up benchmarks in the wrong ways might make it seem like when we achieve that milestone, it's not actually what we think. Okay. One of the early examples of like trying to use AI in medicine was to triage patients. Then you don't have to worry about things like liability issues, but you want to figure out, how in serious condition is this patient, right? Do I need to see them right now or can I wait? And it was, it made a lot of splashes in the news, a couple of years ago when AI beat human milestones. They're better able to triage. Wouldn't that be awesome? Because they're synthesizing all of this past information in which a human doesn't. It turns out one of the ways that they were finding a backdoor to the benchmark was that they were looking at the granularity of the scan. Because if you take the scan on the way to the hospital, then the doctors know you're in trouble. So that's a good way to figure out, you are in deep trouble. And that's, one of the ways that they were able to solve it. So one of the things which is always challenging to me is like, okay, the benchmarks, it's incredible that we have this kind of performance. But, a lot of times the way that we think about benchmarks is if I were a human, the way that I would achieve that, boy, I would have had to learn a lot of different things. That's the way when I give students questions on exams, right, that I do it, is I don't really care if they can solve that literal problem. I care about whether they know the concepts. But when I'm interacting with a human, when they can solve a certain degree of questions, I know that they understand the concepts. When I'm talking about an AI solving it, I don't actually have that knowledge. So it makes me very skeptical about not about whether we've made progress. We've made enormous amounts of progress, but whether we're not putting too much stock into the benchmarks because we're thinking that the way that AI would solve it would be like how a human does.
Just to be clear, the intro of Sparks literally says what you're saying.
Okay,
it's written word for word that, word for word, that it's all about understanding the concept, that you can't rely on benchmarks, that you have to interact with the model. You ask a question, it replies, whether it knows the answer or not. That's not what matters. Yeah. You keep probing, etc. So we're in total agreement. These benchmarks are just a shortcut for us to have a discussion. Yeah. But I think they are absolutely the wrong thing to look at.
Okay.
This is way too cordial. So here's the question. Yeah.
We have the poll results.
Oh, okay.
We have two audience questions.
Yeah, so I have audience questions here in the.
Apologies to.
So this is the pre-debate poll.
Number of votes are on the right.
96 votes. Oh wow! All right. So can we say somebody won? No, we can't.
So there were two questions. With apologies, there were two questions, and I asked that we all try to be quick and because it's clear that everyone has.
They filed questions through the Slido also. So
well, I visually acknowledge both Conrad and Adam.
Okay, all right.
Also Shafi and Amin. So Conrad, you were first.
Yeah, I was gonna probe a little the commitment to scaling. Like at some level, when you say AGI minutes, AGI seconds, and so forth, it's just like a commitment on your side towards the idea that scaling continues. Now, we as scientists have all seen the scaling laws, and we're no longer seeing them because, like, it's clear that somewhere behind the scene of big tech, it's not continuing like that. No, but you have the belief that scaling will continue. I wonder if you can actually defend it.
Yeah. So
Yes, absolutely. So I think it's very simple. It's like the pre-training scaling is kind of, lifting all boats, trying to improve everything at the same time. But I don't know if you've noticed, but mathematicians, they are very good at mathematics, but not very good at other things. So once you want
Excuse
to...
me?
At least most of
I
us.
was told we're not going to be fact-checked in this debate.
So
Finally, something's happening.
it's the same thing with AIs. It's the same thing with AIs. If you want to start to get to very, very high levels, you will start to have to put your scaling into one focused direction. And so that's what we're seeing again with the O1 paradigm, is that we're saying, okay, let's, as a experiment, as a first try, let's try to put this energy into STEM, into mathematics, physics, and those things, and see how far it goes. So scaling continues. It's just not, it's not scaling like that, it's scaling like this, but it's still scaling.
Adam, then Shafi. Oh, did you want to answer? No. Sorry.
Thanks. I just wanted to point out that if an LLM were able to output a proof of the Riemann hypothesis, or P versus NP, odds are we'd be able to check it. And furthermore, I mean, we would all agree that that's a blockbuster result. But I think what's really interesting, more interesting in math or TCS, is that, for example, a definition can come out, and it's very hard to even evaluate whether that definition is important or not, or interesting or not. I mean, maybe Shafi can comment on this, but from what I understand, like, it took years for people to even appreciate probabilistic encryption, which is, kind of stunning if you look back on it. So, LLMs generating, for example, distribution definitions. I mean, we can't even agree on what theorems are interesting these days in ML theory. It's quite possible that it leads us towards definitions or theorems that, maybe just aren't that interesting.
I think somebody else should answer, but I just want to say it's kind of, I mean, the premise of the debate is a little wrong. Like, mathematics is not about proving theorems. That's not the game that mathematicians are playing. It's about understanding. And understanding, it does come through those definitions, and evaluating understanding is much harder. And it would be an entirely different discussion if we were trying to answer that question. Will AI be able to make progress for us in terms of understanding? That's kind of a different question that we haven't answered in this debate.
Shafi, you had a question?
Or did somebody else want to comment first?
I guess what I really liked what you were saying about focusing on, let's say, one paper or one piece of work, going and sort of giving instructions. Sort of, what are the different? How would you change definitions? What do you understand from this? What are the questions they didn't ask? What questions you would ask? But it seems to me that's not the LLM. It's you, as a mathematician, directing the LLM to do the kind of things you do on, super scale, turbo. That I wouldn't call that the LLM proving or getting a new understanding. It's the two of you together. So, I don't know, does AGI mean that?
No.
Oh, okay.
So I want to answer this. This is really, really important. This is the most important sentence that I said. So I will just repeat. Like, that's not what's happening. We're not telling the LLM, go read this, try to rethink the definition. I think that makes a lot of sense to try to do that, but that's not what's happening. Everything that happens, I will say again this sentence, is very scalable. It's emergent. So the model decides on itself to do those things. Why does it decide to do those things on itself? Well, probably because of the pre-training, because out there on the web, there are probably some people who said, hey, that's a good way to study a paper. Why don't you do, these steps? And it kind of remembers it from that time, and now it applies it. That's a big, big, big difference. Big, big, big difference.
I think it's important that it comes from pre-training though, right? Like, if we think about, will behaviors emerge that are superhuman, then I think that's still a very open question, because like, if it never saw, like, it saw backtracking, it saw like double checking in pre-training for sure. And then RL can like get it to be very consistent at that. But like, I guess what we want is real exploration, like beyond pre-training, right?
Yeah, and so you had mentioned earlier how pre-training might not be as helpful for math necessarily. I think this raises a potentially funny scenario where pre-training might actually be harmful for some of these unresolved problems. because the internet is full of all sorts of dead ends where people were trying to prove whether P equals NP or the Riemann hypothesis. And so it might be that the pre-training data would predispose LLMs to try those same types of strategies, because when people are trying to prove these conjectures, this seems to be the kind of thing that they do. But we know that those directions don't work, or at least if they do work, it's really not in an obvious way. And so they might actually be harmed by having that historical baggage in their pre-training data.
I mean, you had a question? Yeah, let me just, Ankur, can I borrow it?
Thank you all for all the comments. We expected more, right? But still,
more fireworks.
Yes.
Okay.
One comment or question that I'm struggling with is that why do we think that? So the way that we lift the weights by cranes is not exactly. The way they do it is not exactly how we do it, or the way that airplanes fly is not exactly flapping wings, right? Why do we think that the way that we have to do mathematics or proofs should be the way that humans actually do it, right? It's like why do you think that there are these steps that we have to take? Because all the mathematicians told us they're taking these steps, but maybe these are not necessary steps in order to actually come up with a new proof, right? So I don't really understand, this emphasis of like why the way that humans do it should be the way that even machines or LLMs or like emerging abilities, should come about.
Yeah, and I think it's not clear that it should be that way, and that's why I think maybe it shouldn't be LLMs that are actually like our best models for mathematics specifically. Like again, I guess for chess, we have models that are very much not doing it like in a human chain of thought type format and are very superhuman. Maybe like the only argument for doing it in a human way is if we care about like trying to understand the proof then and like trying to extract some definitions and things like that, then we want it to be human-like or human readable at least. But I think like if we care about proof power, like being able to prove things, then I don't think it has to be in a human-like way.
So we have just a few minutes left. So Umesh, can I just ask one question from here and then we'll come to you? Can you guys speak about verification? How do you expect LLMs, current and future, to do checking proofs, even adversarially constructed fake proofs? So.
Yeah, I mean, I think this is like a general area. For example, in the alignment literature, there is a scalable oversight area, which is generally about like training models to find issues in arguments, like or debating, for example, like adversarial settings where one model is trying to kind of find issues in what the other model is saying. So I think that's one approach, and another is maybe employing some symbolic things like lean proof verifier type things to check proofs if they're written in a formal way.
Maybe I just want to reply to the previous question or comment by Amin. I think there is also still like, if you really believe in this AGI timeline and second minutes, etc., there is still a safety aspect that maybe you don't want those things to go totally off the rail and think in totally completely novel ways that are absolutely alien to us. So I think grounding into the human thinking is not such a bad thing. We don't care so much about the Riemann hypothesis. We care, but again, what we care about is the understanding that it will bring us. It's what Ankur said, that it will open up a new era for mathematics. It's not necessarily the proof itself. Like the proof power is irrelevant. It's really, the understanding that it would bring. So I like to ground into the human thinking.
Amish, you have a question?
Yeah. When I think about mathematics, I think, well,
your mic is not on.
Sorry. Yeah. So when I think about doing mathematics, I think about abstraction, different representations, visualization or building a model, things like that. And so just to try to understand, why, in what way you would think that LLMs or, some some close cousin of those would be able to do something like this. Let me try to pose it concretely like this to create a toy model, where we say, look, let's concede that LLMs are really good at doing language, but language in a very generalized form, not just English, but any language, programming languages, poetry, anything that we think of as language-like. They also, let's think of this entity which knows language in this very generalized way and has access to all the knowledge on the internet and can interact with it. And let's throw in also some other abilities which are not, which we think of as rounding it out in some ways. So we won't quibble about little details. So can you say what LLMs can do which dramatically are dramatically more than that?
Maybe it's too strong what I'm going to say, but language is mathematics. I mean, mathematics and language is the same thing. Language is about abstraction. A word is a definition. A word is an abstraction. So it's not, when you talk about this generalized language, to me, generalized language includes mathematics. It's not, it's the one and same thing.
Okay, but I understand, and I understand why you'd say that, but let me just say that, okay, you do need a lot of abstraction in language, but let's put that into a black box and say, LLMs, they were great at doing that. They had to abstract, they had to do a lot of stuff, but now let's put it into a black box and say, this much abstraction and no more. Now, any other abstraction you get in terms of mathematics, creating models, creating all that, let's do that from scratch. So that's the toy model I'm giving you, and I'm saying, look, can you show me things that you do with LLMs, in your Sparks paper, any, Sparks 2.0 or 3.0, is there any ability you can point to which is substantially beyond that, without quibbling about small things that.
I mean, my favorite example remains Tixi unicorn, and especially the manipulation when you remove the horn. So again, let me just repeat this experiment. So it draws a Tixi unicorn. I think that's amazing. It's not out there on the web. Great. But now you don't stop there. You do this interaction with the model, try to check whether it really understands what's going on. So you scribble the code, you randomly permute it just in case it took it from somewhere. So now you have code totally random that draws a kind of slightly weird looking unicorn, and you remove the horn and you just give the code and you say, this is supposed to draw a unicorn. Can you put back the horn? This, you have, like, the model has to understand the code. It has to put back, it has to connect, it has to do this abstraction, connect, okay, it has read about unicorns, it has a horn, the horn goes on the head, it has to calculate the point, a point on the sphere on the head, connect it there. I mean, this is a smoking gun example to me of an abstraction which is beyond what is literally in there.
So, sorry guys, can we leave that question there? I think for your sake, Seb, we have to stop now because you have a hard stop coming up. So one more question. We will have Misha ask a question, and then a quick one, Misha.
Thanks. Great discussion. It's I guess when we sort of tried to when we were discussing the topic of the debate, we tried to come up with something which would sort of symbolize some sort of very high level of creativity, sort of at or beyond what like the best of humans can do, and we tried to so P versus NP or Riemann hypothesis were chosen because it's a like really hard problem. A lot of people thought about it and so far haven't succeeded. What would, but you can imagine many other things, right? Like, but would be kind of hard to agree on what they are. Would you have some sort of idea what would be like really convincing example of creativity, maybe going beyond necessarily mathematics, maybe non-mathematical thing, to like symbolize this top human or superhuman achievement?
The Go is a good example. The famous move, in Go is, I think, a good example.
Tom, you have some?
Yeah, I mean, I think this would be much harder to quantify or decide whether it qualifies as creativity, but being able to produce creative works, such as a novel that becomes very popular, I think would also be another very important side of creativity.
Great. I think you have
to say one last
right.
sentence.
Sure.
Sorry. Which is just so I know you guys were expecting a lot more, disagreement and sparks, but I think this is a testament to what's happening. The fact that if we had this debate even a year ago, it would have looked very, very different. Of course, there are also some people on campus that would have made this debate different even today. But the point is, this is really insane that we're getting to this stage, debating whether we're going to prove the Riemann hypothesis or P versus NP. Of course, it's very far off, but still, I think, certainly I agree with what everybody else said. Again, the conclusion that we draw from them might be slightly different, but we're in agreement that we have gone, beyond memorization, these things really generalize, this thing really think, reason. I mean, this is really crazy. And I'm personally very, very happy that we have moved to this stage, finally.
So that's a good place to end, unless Ankur, you have one final thought, like two, you seem to be itching to say something, so.
Sorry, yeah, I'm not sure I agree with the, that discovering a new novel that's popular would be the mark. I mean, we also have a lot of things like Brahms' Lullaby, the way that it works in terms of the 4-chord progressions are used all throughout music. Like we have AI that produces pop songs that's popular. So somehow the things that are popular sometimes can be more pattern recognition than they are deep understanding. To me, I can't put a particular goal, but what's amazing about the AlphaGo moves is that you have some knowledge that's beyond just that particular game configuration and scenario that's generalizable. So humans learn something that they can take with them as a new move. So in mathematics, it's not about the literal theorem, like here's a statement that you can use. The mark would be like if it actually taught something that's generalizable and usable to human mathematicians, that would be incredible. Whether it's something as ambitious as Riemann, and we can all just go home and stop, or even if it's something more tame than that, that would still be amazing.
Great. Well, thank you very much, guys. There's a audience question that has got lots of requests. How did the audience opinion change before and after comparing the two polls? Someone is curious about that, and a lot of people want to know the answer to that. Can we have the polls again? Yeah. Oh, sorry, you packed up there?
I can do it.
Yeah, all right. But in the meantime, let's thank our debaters and panelists. Thank you very much. Yeah.